Hello everyone, welcome back to the channel. Today we've got yet another systems design video for you. Now before we go ahead and get started, let's play a quick game, which is am I A, intoxicated, or B, tired? Unfortunately, because it's a Wednesday, the answer is going to be tired, which is why I want to get through this one kind of fast. So let's go ahead and get started. Alright, so let's go ahead and get into it. So, unless you're watching the super secret Jordan Has No Life OnlyFans version of these systems design videos, you're probably watching this on YouTube, which means you at least understand the product that I'm going to attempt to be building here. YouTube and Netflix is just going to be a video watching site where a given channel or a user can post a variety of videos, they can watch a variety of videos, and such an example would be one right here where the video has a title, a number of views, can have some comments. It's able to buffer in real time as your network bandwidth fluctuates. And so the gist is that we're going to attempt to build something like this that actually scales to billions of users. So let's go ahead and outline some problem requirements. So the first is that users can post videos. The second is that users can watch videos. The reason I have the arrow here is because we're going to be watching a lot of videos, as one does. Users can also comment on videos, and users can also search for videos by name. The reason I'm not really doing views as much in this one is frankly because if you watch the tiny URL video, the process that we would use to be aggregating video views is very similar that we would be using to aggregate tiny URL link clicks that we use in that video. So I think it would be redundant. I would just recommend you go watch that video as well if you're curious on view aggregation. So again, number 2 is going to be the most important, number 2 being that we can watch videos. So we want to optimize for our read speeds. So let's go ahead and quickly outline some capacity estimates while we're at it, because I said we're going to be building for large scale. Let's imagine our product has 1 billion users. I wish I would be retired right now. In addition, our average video is going to have around 1,000 views. That being said, some are going to be super popular, right? Certain channels, such as myself, of course, with billions of subscribers, have millions of views per video. Additionally, we've also got videos being around 100 megabytes on average. There are about 1 million of them posted a day. And if we were to go ahead and figure out how much storage that needs to basically hold all of these videos, we can take that 100 megabyte size per video, multiply it by the 1 million videos that are getting posted per day. We can also multiply that by the approximate number of days per year. I use 400 instead of 365, and that comes to about 40 petabytes of storage per year. Now obviously this is going to be a ton. That being said, when you're making a crap ton of money, that's doable. You just get a lot of hard drives. So before we actually go ahead and get into any design or server choices or database schemas or anything like that, let's go ahead and do an introduction to video streaming. So the first big concept that we have to think about is that we are going to support streaming, or rather watching footage on many different types of devices, right? I might be able to watch on my phone, you on your laptop, someone else on their tablet, and basically the gist is that we may have to support many different types of them. Additionally, we have to be able to support different networking speeds, right? Me on my gigabit Ethernet is going to be able to watch clips at a higher rate than you can on your 2G cell phone. So as a result of that, what would be really, really great is if certain devices with different bandwidths or different abilities to load footage can actually load them dynamically, right? So for example, a slow phone might first be watching some footage in 480p, switch over to 720, maybe they get slower again, go back to 480. A medium device might be fluctuating between 4K, 1080p, 720, and then back and forth. And then a super fast connection might just be able to watch the entire video in 4K, which would be great. So the gist is that in order to do that, we need to basically be able to support multiple different resolutions for our clips, and also to support different devices, multiple different encodings. Okay, so let's talk now about video chunking, which is going to allow us to do this in a more efficient manner. So keep in mind that we want multiple different resolutions for every single clip. We want multiple different encodings. And what that really means is that when we upload a clip from our device, let's say I'm posting a Jordan Has No Life video, YouTube is going to take my video and make multiple different copies of it, right? We would need a 1080p version, we would need a 720p version. And if you're a device and you want to constantly be switching between those two as your kind of bandwidth is scaling up and down, or your network speeds are scaling up and down, we would want to load both of those clips. And the problem with that is that we don't need both of those clips, right? We only need the parts that don't overlap with one another. If I've already watched, the first quarter of the clip in 1080p, then I only want to load the remaining 3 quarters in 720p. And so the way that we can do this is actually by splitting all of our videos into chunks. So for example, if I've got my 1080p and my 720p video right here, maybe I can watch the first 2 chunks in 1080p. My device then realizes its network speeds have gotten worse, so it's going to say, hey, let's load the 720p chunk after that. Oh wait, it got better, let's go back to 1080. Oh no, worse again, and do 720 for the last 2. So the fact that we actually have all of these different chunks means that with a relatively small granularity, we can pick the right chunk at the right time so that we can take advantage of our changing networking speeds. So let's quickly outline the different advantages of splitting our videos into a bunch of different chunks. The first is going to be parallel uploads. So imagine that this were our server or our backend or S3 or anything like that, basically wherever the chunks are going to end up. If we can do this in parallel, we can effectively just establish multiple different ports for this guy to be connected to, and as a result of that, we can just send the chunks on different ports. Not really a huge deal. Frankly, I'm not even sure this would increase speeds very much because your bandwidth might be limited from your device, but no big deal. The bigger thing, on the other hand, is there is a lower barrier to starting a video. So rather than having to load this entire huge file and get it on your device, what you can actually do is load just the first chunk of it. Once the first chunk is loaded, we can start watching, and then from there we can start loading the second chunk, the third chunk, and the fourth chunk. And so when you think of it, that's why on YouTube, you can get partway through a video and then it might start buffering. We're only loading a little bit at a time, and then asynchronously in the background loading the rest of it. Okay, and then of course, the last thing we just covered on the previous slide, which is that as our networking speeds change, we can grab the best chunk for us. So we're going to do so based on our current networking abilities. And as a result, we now have a bunch of different chunks per video. We're going to need some sort of table or some sort of database to keep track of all of these chunks because things are going to get complicated when we have so many different copies of every single file. Okay, so let's start outlining some of the database tables that we'll actually be able to use for our service. I'm not going to go into these in too much detail. I'm going to outline a schema and then possibly suggest an actual database choice here. But I think it's worth noting that because a lot of these are not going to be the main bottleneck in our system, we don't have to overly optimize on them too much. Just choose a decent schema and be reasonable about that. So first, let's start with a subscribers table. So imagine that we have a user ID and another user ID that describes who we're subscribed to. This is going to allow us to say, if I'm Jordan and I'm a viewer of YouTube videos, who am I actually subscribed to? That's going to be a query I have to run pretty frequently when establishing something like, the equivalent of my news feed in YouTube. And again, I'm not going to describe how we would actually build something like that out because we've basically already made a video on that, right? It's the same problem as like the Twitter, Facebook, Instagram, Reddit problem. And it's the same exact thing where, when a video gets published, you would actually deliver it to all of these caches based on who you're subscribed to. So again, not going to cover that too much. Just watch the Twitter video if you're more concerned on how to build something like a home screen or a news feed. But we do still need this subscribers table for a different reason, which I'll cover later in the video. So the nice thing about that is because we want to know, I'm Jordan, who am I subscribed to, we should probably index on the user ID field so I can quickly find all the people I'm subscribed to. And we should also partition on that user ID field so that all of the queries to figure out who am I subscribed to go to the same physical node. Additionally, if we really wanted to, another thing that we should know is if I have a YouTube channel, as I do, who's subscribed to me? Well, the nice thing about this is that so we don't have to make a kind of, two-part write every single time someone subscribes to someone, we can use change data capture instead to ensure that eventually our second table will be updated, right? And we can do this using Kafka, as we've done so many times in the remainder of these videos, and Flink. So if we have all these subscribers right here, we can actually partition Kafka on this subscribe to field. And then that way, if user 10 has a YouTube channel, you can see that they have subscribers 3, 6, and 5. Those all get added and cached locally in our Flink node. And we can either make a second database table out of that, or we can just cache it, which personally I would like to do for later purposes in the video, and I'll explain that down the line. So this is going to come in handy when uploading videos. We'll talk about that in a bit. The second, third, and fourth tables that I wanted to talk about, I will now get started on. The first is going to be user videos. So this is just outlining, if I'm a user, what videos have I actually posted. That's going to have a user ID, it's going to have a video ID, it's going to have the timestamp that we actually posted that video, and then of course some metadata about the video like the name and the description. So of course, for a given user, we want to be able to quickly figure out all of the videos that they've posted, and we should do so by keeping all of those entries on one single node. We can do that by partitioning on the user ID, and then using some combination of the user ID, the video ID, and the timestamp as either a sort key or an index, so that I can basically quickly figure out all of the videos that I've posted in order by the time that I posted them. So that should hopefully be self-explanatory. Again, most of these tables I'm not really too concerned with performance-wise, because we're more concerned with actually watching the videos, not really loading the metadata for them. Okay, next we've got a users table. Don't worry about this one too much. Let's keep it simple. We've got a user ID, an email, a password, whatever other information you have to store. And of course, if we partition on our user ID field and index on our user ID field, it should be relatively easy to figure out where a row for a given user actually lives and not have to do some sort of distributed query. The last aspect of at least this slide here is going to be the video comments table. So for this one, we've actually got a video ID, and I should preface this with saying that in reality it would probably be like a channel ID and a video ID, because eventually that's how I'm planning on uniquely identifying a video, is a combination of just some channel name and then also the video ID that comes with it. And so we can partition on that so that all the comments for a single video go on the same node, and then we can also use the timestamp as part of the index so that they're sorted by timestamp, and of course have the actual comment poster ID, the content, etc., etc., etc. So another thing that is worth talking about is actually going to be our video chunks table, where as you can see, we now have a bunch of encodings and resolutions to worry about. Now I've pretty stupidly actually switched the order of these, so H.264 would be the encoding, 1080p would be the resolution, but the gist is that by partitioning by video ID, we ensure that all the chunks for a given video should be on the same node. Additionally, by sorting by the video ID, encoding, resolution, and then after that, the chunk order, we can basically say, hey, you know, if I have really good internet and I can watch every single clip at 1080p on the H.264 format, what I can go ahead and do is just load all of them. They'll be right next to one another on disk, and that should be a simple query. So again, that's going to allow easily getting all the chunks for a given resolution. Even if we can't load all of the chunks for a given resolution because our network speeds are fluctuating, it's still a pretty easy query to go and get the ones from the other resolution. I wouldn't really worry about it all too much. And then of course we would have some sort of hash to describe the chunk, and then possibly the URL to wherever we're storing it, whether that's S3 or Hadoop or something else. So let's actually talk about some database choices that we want to use for the aforementioned tables. So the main thing to note is that we're going to be worrying about reads a lot more than we're worrying about writes. And typically when we're worrying about reads, what we basically want to do is keep our database schema simple and, cache where possible. And, we can get away with using something like MySQL here because it actually uses a B tree. So if you recall, the B tree is just a big tree on disk. And it is a lot easier to iterate this on disk tree than it is to check multiple different SS tables, which would be the case for an LSM tree index. And so something like a B tree index would be perfectly acceptable here. And as a result of that, I tend to opt for something like MySQL for all of those tables that I listed. The one caveat being that some videos may actually get a lot of comments, right? Because at the end of the day, if it's a super popular video, the first 10 minutes you may get a ton of comments, and MySQL might not be able to handle that type of writing load. So for that type of situation, I think you could make the argument to actually use Cassandra here for a couple of reasons. One, the LSM tree architecture means that all writes first go to memory. The second thing is that it's a leaderless architecture, right? So as long as we partition by that combination of like channel ID and video ID, we can partition by that, and then the timestamp is actually going to make it such that no two comments are exactly the same. And we're not really going to have to deal with any write conflicts unless, of course, we support comment editing or we support child conflicts, because then we can have dependency issues where, let's imagine I wrote a comment to this replica and then I try and edit it, but that goes to this replica before the comment itself already exists. Then Cassandra might be problematic and we might have to look for a different solution. But assuming we just allow writing comments, we don't allow editing them, and we don't allow replies to comments, then we shouldn't have to worry about using Cassandra. It should be okay. Okay, the next step that we're going to start to actually talk about is video uploads. Now these are going to potentially get a little bit complicated, but the main idea to remember here is that we aren't uploading to our database very, very often. Again, I upload once per week, for example, and I watch many, many more YouTube videos than that. So if we're uploading very infrequently, the idea is to do as much work as possible on the write path and as little work as possible on the read path, because most of us are just watching videos the majority of the time. And the main idea here is we want to keep these relatively cheap, and when I say cheap, I mean literally cost-wise. Let's keep them cheap and also correct. If I'm uploading a video, I expect to see it eventually. It doesn't have to be instant, but it's got to be up there eventually. So the idea is for each chunk, we've got to do some sort of post-processing on it, right? Because we want to store multiple variants. We might have to store a 480p version, a 720p version, a 1080p version, and all of those things are going to require us to store multiple copies, as well as the different encodings. So again, we can basically maintain a list of servers that are going to do this processing for us, and it doesn't really matter which actually does the processing, as long as it eventually gets done. So with that being said, what can we actually do? Well, for starters, we know that processing these events takes time. Actually converting a video from one format to the other is relatively compute heavy. Same goes for encoding it to a variety of different formats. And so we're not just going to like upload a video to a server and be like, hey, do this synchronously and then get back to me whether or not it worked. We're going to have to do this in the background of our application. And typically when that happens, we're going to need some sort of message broker. So assuming that we put events on a broker and process them in the background, what type of broker should we actually use? Well, let's start to think of it. Remember, I said already that we don't actually really care which one of this guy, or this guy does our processing for a given chunk. So what type of broker should we actually use? Well, in this case, I think what we would want is probably going to be an in-memory message queue. So if you recall, at least from our concepts videos, the reason behind using something like a Kafka broker or a log-based message broker is that there's only one consumer. And because there's only one consumer and because all messages are replayable, we can actually build up some state on our consumer. The issue with something like an in-memory broker is that you don't really know that the order of the messages is going to be consistent, especially if they get replayed. And in addition to that, it might not be as durable. You can use things like a write-ahead log and replication of your broker to ensure that every event gets played once. But if the gist is you want to be able to maintain the same exact state if your broker were to go down, then it is going to be the case that you would much rather use Kafka. That being said, we don't actually really care about state because all our consumer is going to do is read file, process file, and then write file. And so when you're just reading a file, processing, and writing it, we don't actually care what happens from message to message. Everything that we need to know about what we're doing is encapsulated within one message, and so we don't have to maintain any state. Additionally, we want to get this process done as fast as possible, as long as it's not going to make us sacrifice read speed. So as a result of that, using something like an in-memory message queue can allow us to use some sort of round-robin load balancing, where basically as each of these guys is ready to take an event, they can pull one off the queue, put it over here, right? So no one else is going to get it. And then when they're done, they can reach back out saying done. And then finally, this event is going to get deleted from the message broker. And so for that reason, I definitely support using an in-memory message broker for this type of task. Something like RabbitMQ, Amazon SQS, any of those types of solutions I think would work great here. ActiveMQ as well. Okay, so now let's go ahead and talk about chunks. So keep in mind that we now have this message broker right here. We've got a bunch of processing nodes that are reading from the message broker. And the question is, what do we actually put in the broker? Well, the answer should be certainly not the chunks. The reason being that the chunks are going to be decently big. They might not be multiple gigabytes, but they might be a couple hundred megabytes. And as a result of that, they are probably too big to actually put in the broker. And so ideally what we would first want to do is upload them to some sort of either distributed file store or some object store. And then after doing so, we can put a reference to them in the broker, right? So for example, chunk goes here, and then we say like chunk at some URL, and that's going to be going into our RabbitMQ. Now it is possible that we can have partial failure states here, right? Where 1 is going to go through and then 2 doesn't go through. The big thing to note there is it doesn't really matter, right? Now we're storing a few extra chunks, but at the end of the day, we can always run some sort of background cleanup job where we go through S3 and we would then basically say, do we see this in our chunk metadata table? If not, get rid of it. If we do, then keep it. So I think that is preferable to having to do something like a two-phase commit right here, which basically we want to avoid at all costs unless we absolutely need it. So the question now is, we know we're putting our chunks somewhere. Where are we actually putting them? Well, I think we've got a couple of options. The first is going to be HDFS, or Hadoop Distributed File Store. So HDFS would be run on a cluster of nodes like so. And what we could actually do if we really cared about our, our processing speeds is we could actually run our, our consumers or our processing nodes that do the encoding on HDFS, right? So, we might devote some resources to processing, and in addition, some resources to actual storage. And that is something that we can do. And so the nice thing about that is we would get really good data locality, right? Because all of these guys are probably in the same data center, or at least similar to one another, they're going to be able to process and write these chunks back to HDFS super quickly, compared to something like S3, where you've got S3 over here on the right, and every single one of these nodes is going to have to be making networking calls multiple different times to load every single chunk from S3 and then write it back. So HDFS is probably going to be the optimal solution if we care about our write speeds. However, it is worth noting that in practice, two big things come up. One, HDFS is just like objectively more expensive, right? So S3 is going to be cheaper. Another thing is that truthfully, in modern computing, or at least from what I understand about modern data centers, we're actually going to be a lot more CPU bound than we are network bound. And so even all of these calls are going to be expensive, even though they're going to be expensive. What's more important is the fact that this is just going to take time. And when you look at the amount of time relative to the networking speed versus the CPU speed, it's actually probably going to be more significant on the CPU end, and we probably won't notice as much latency as a result of basically those networking calls. And so considering it's cheaper, considering we don't really care that much about making these writes or these uploads super fast, I actually am going to go with the S3 solution. I imagine this is probably more similar to what these companies are doing in real life. Okay, so now this is where things start getting kind of complex, which is that we are going to talk about aggregation. So we've got a bunch of different processor nodes, right? Processor, blah, blah, blah. And they're going to be outputting a bunch of different copies of every single chunk. And considering that these are all distributed nodes, how can we actually figure out when a video has had all of its chunks finished processing? So this is kind of the solution that I came up with. I think this would probably be the most controversial part of the video in terms of people trying to correct me in the comments. So please feel free to go ahead if you want to. But ultimately, this is the solution I'm going to go with. So the first thing is that imagine we've got 3 chunks to upload. Like I mentioned, the first thing that we're going to do is literally just put them in object storage, which is going to be S3 right here. Once that has completed, it needs to actually finish, we can then go start enqueuing the metadata for all of those chunks in RabbitMQ. So we would say, like, chunk 1 is s3.com/abc, chunk 2 is s3.com/def. And then in addition, in parallel to uploading these events, we would also upload a second event over here to a different Kafka queue. The reason I use Kafka is because we want to maintain this to keep state over here in Flink, which I'll explain what that does in a second. So the type of message that we would send to this Kafka over here is this guy. Imagine we have video 10 and we're uploading that. I would basically say in advance, hey, video 10 is 3 chunks. That's what we're going to be looking out for. So then we can have our Flink over here, which is going to be keeping state. The reason I use Flink, as always, is because it makes sure that every message actually gets processed at least once. So even due to failures or anything like that within our system, eventually it'll come back up or another node will take its place and the message will still get processed. So video 10, we've got 3 chunks. It means now that this guy knows that video 10 has 3 chunks coming in, and it's actually going to be able to wait on them. So I could say video 10 is 3, and then imagine chunk C isn't in yet. Once I see chunk A and once I see chunk B, we're still not done. Eventually chunk C gets over here to Flink, and then we say, okay, actually we're good to go. How does chunk C get there? Well, all of the processors, once they're done completing their actions, are going to first do two things. One is that they're actually going to, let me switch up the order here. One is that they're going to upload that chunk information to Kafka, basically saying, hey, we finished enqueuing this. The second is that they're going to go back to RabbitMQ and say, hey, get rid of my chunk. So I no longer need to process this thing anymore. It's completely done. I've alerted Flink that this entire process is complete. And so now what's going to happen is that it's going to get dequeued from RabbitMQ. It's going to get inqueued to Kafka over here, and it's going to go onto Flink. So when this state is kind of completely filled, which is that we have the amount of chunks for the video that we think that we have, we're complete, and we can do all of the downstream things that we actually need to do. Now, the nice thing about this is that you may say to yourself, oh, Jordan, there's tons of room for partial failures here. And you are correct about that, right? You know, this step could fail, this step could fail, and as a result, you know, we might end up replaying one of these events, we might end up replaying one of these events. All of these events are idempotent, which basically means that even if we were to do it again, it would actually have the same effect as if we had only done it one time. So again, if I'm never able to actually dequeue this event from RabbitMQ, if that fails, what would happen is it just gets reprocessed, it gets sent right back to S3, we then go back to the Kafka queue saying, hey, we've just completed this chunk again, and then even if that was already present on the Flink node would say, actually, I already have the data for this video and for this chunk, I'm still good to go, you know, I'm not double processing this video, I understand it's a duplicate, this is totally fine. And so through this, all of these things are idempotent, and our thing is completely fault tolerant, or at least I should hope. Okay, I did all that, but it was a bit abstract, so let's go and actually talk about the data models that we might use putting into each of our queues, which should hopefully make this a little bit more clear what we're actually doing. So we've got our client over here. After uploading to S3, the client is also going to put some data in RabbitMQ. So the first idea is that, again, we've got kind of our user ID because we're sharding by user ID and video ID. And so basically, let's imagine user 10 is uploading video 100. This is going to be the first chunk. Here's the S3 link that we got after uploading it. We can put that in RabbitMQ. The processor is going to process it. And from S3, it's going to say, hey, get me s3.com/10/100 ABC. S3 is going to respond to it. And then from there, it's going to basically put in Flink, hey, here's chunk number 1 of video 10 or video 100 for user 10, and then it's going to actually provide a list of all the different chunk copies that it made. Their encodings, their resolutions, their hashes, their new S3 URL. It can actually put that in Flink. In addition to that, we've got this second data model right here, which is more about the video metadata, right? So for user 10, for video 100, there are 3 total chunks. The name is going to be Jordan's feet, and the description is that they're so stinky. Wait, that says dainty. Freudian slip, perhaps. So anyways, we're going to put these in Kafka, and then they're eventually going to flow over to Flink. It doesn't actually matter whether this message gets to Flink before this message does, because at the end of the day, both of them are going to be required for us to consider that video completed. We're going to store this data regardless on Flink, and we're going to store this data regardless on Flink, and then we're effectively going to do a join on them via the user ID and the video ID fields, and use this numchunks field right here to determine when we're done. So hopefully that clears things up a little bit. But we've still got plenty more to do as far as video uploading goes. We can actually tell when a video has finished aggregating or when all those chunks have been processed as necessary, but now we have to go to all of our databases and actually say, hey, here's the data that you were looking for. So again, we can now begin to update our derived data. Oops, had the eraser on. So we're updating our derived data, and at least to start, we're going to put it in 2 places. The first is the video chunks table, right? We've got now this massive data model, and we want to upload it all at once, atomically, into a single partition. We can do so by just partitioning by the user ID and the video ID, so we make sure that for a given video, all of the chunk metadata is on the same table. After those video chunks are uploaded, we can then basically go ahead and say, hey, let's now upload to user videos. So now we'll say, oh, user 10 has video 100, and the name is Jordan's feet. Now, if you notice, there is technically a partial failure scenario here where this guy goes through, number 1, when we upload to the chunks table, and number 2 goes and fails. That being said, because this is Flink, we know that we're not actually going to consider this event completely acknowledged until number 2 goes through. So even if number 1 does go through and 2 fails, there's going to be a small period of time where this table is not as up to date as this table, but you can only really find that a video exists if it's in the user videos table. So you're going to have a bunch of chunk metadata existing in this table, but no one's actually going to be able to watch the video because they would have to access it through the user videos table and like going to a user's page and clicking the video. And so as a result of that, we basically wait for a little bit. This guy eventually comes back up, or someone else takes over the state. It retries the event until this guy goes through and this guy goes through, and then we're good to go. Of course, this is totally fine as long as all of those writes are idempotent. Because those chunks, or the data for those chunks, is going to be the same data, from both before and after this Flink node crashes, it's just going to overwrite itself, no big deal. Same thing for the user videos table. So again, no big deal. So this is why the order is important, right? If I had the user videos table first, it might look like I have actually posted a new video, but then when you click it, you can't load any chunks for it. So again, that's why I've deliberately chosen to upload the video chunks before the user video metadata. Okay, lots of video uploading details for this one. We've got plenty more to go. So basically, the next part of this is that some of our videos, we actually know in advance that they'll be popular. So this is pretty cool because for a lot of social networks or social medias, it's very hard to say in advance whether a post is going to be popular. If I'm blind and every single person that's posting is an anonymous user, when a new post comes in, I have no idea whether people are actually going to view it a lot or I don't. That being said, with a service like YouTube or with a service like Netflix, we actually have the privilege of knowing when a particular video is going to be popular in advance, precisely because we know how many subscribers they have, right? So let's take my channel, for example, with my 1 billion subscribers, and we can basically say, hey, if Jordan's posting, let's go ahead and push this thing to a CDN, so that way when users originally try and load it, those chunks are going to load more quickly. We can go ahead and actually do just that. But how would we do it? Well, in the past, you might have thought, okay, well, this guy is just going to be partitioned by video ID, right? We're sending video metadata, we're sending video chunks, and at least intuitively, it would make a lot of sense if we partitioned both the Kafka queues by video ID and also if we partitioned Flink by video ID. However, what I'm now proposing is that rather than do that, we should be partitioning everything by user ID. The reason being that the subscriptions table can be partitioned by the user ID. So basically for my user, I know exactly who is subscribed to me. And as a result of that, now I know, Jordan has 10 subscribers. And here are his new videos. He's got this guy right here with video 1. It's got 3 of 3 chunks. He's got this amount of subscribers. Oh shoot, that's actually going to be a very popular video. So not only are we now uploading to the video chunks table, then the user videos table, but lastly, we can even upload to the CDN. I think again, precisely the ordering is important here because if these two succeed and then the CDN fails, now all of a sudden you can still watch this video. It's just going to be a little bit slower. We can always do a pull-based approach into the CDN rather than a push-based approach, but eventually it will get pushed to the CDN because of how Flink works. So again, if we were to publish to the CDN, for example, first, then all of a sudden we're taking up a bunch of room in our CDN and the video's not even watchable, or just it would be a bad situation. So be careful when you're doing these kind of sequential uploads to actually think a little bit about what the ordering means. Okay. Let's now talk about actually building a search index. So this is also going to be a little bit complicated. I think I would rather do this a bit more in depth in a separate video. So I'm not going to go too crazy with this one, but hopefully this should outline some of the problems that you have to consider when building a large, massively distributed search index. So for starters, we want to take our video title and we want to take our video description and make sure that if anyone searches for that video title or for that video description, that they are easily accessible and that that query is going to be quick. So the way that we do this, if you've watched my concept series, is via an inverted index. So for example, if we've got video 22 over here, and this is the title of it, we would want to split out the main tokens, like these guys right here. And then we would go ahead and basically say, hey, for this given word, here's a list of video IDs that actually contain that word. Now, of course, as you can see, I only kind of took like the 4 non-common words right here, but how you actually break this document up is going to depend on the tokenization process of the search index that you actually use. Okay, so the next thing that we need to think about is partitioning, because partitioning and the actual speed of our query is directly dependent on, just how well we balance out our data. If we can keep all queries going to one single node as opposed to having to aggregate them over multiple different nodes, that is going to be a lot faster. So again, ideally, for a given search term, we would want the user ID and video ID combo on a single node. The question is it possible? We've actually discussed how much storage we have available. We've discussed how many videos we've posted. Can we get this done? Let's say if we post 1 million videos a day over 10 years, that's about 4 billion videos. So if the user ID and the video ID are integers, that means combined, they are 8 bytes in total. So 8 bytes times 4 billion is 32 gigabytes of IDs for a search term. In theory, that is actually super possible. However, in reality, keep in mind that if we only just store the user ID and the video IDs, we can get those back, but then we would still have to do a distributed query on our video metadata table in order to actually get all of that data back when we actually make the search, right? Because even though we have this data, we still have to get the names and the descriptions and possibly the thumbnails of those videos. And so in reality, it's probably going to be a lot more than 32 gigabytes of IDs for a single term. And as a result of that, we're probably going to have to do more partitioning than this. So we've got basically a couple of decently solid options. The first being that, we don't do any term-specific partitioning, and rather we just, kind of round robin all the documents and then keep a local index per partition. That can be okay, but if we have too many partitions, let's say we have 100 different partitions of search indexes, then now we have to aggregate 100 different partitions of indexes, which is, probably going to be pretty expensive. Another perhaps hybrid option is that, where we can store all the terms on one single node, that we do. That being said, for very popular terms, take Fortnite for example, we can actually do an inner shard on that and keep, all the Fortnite documents on a combination of 5 nodes and then, have to aggregate those together. So let's do some search index partitioning continued. So the idea is that in reality, we're going to have to store, a bunch of metadata for the video. We're going to have to denormalize our data a little bit, or else we're looking at potentially a super expensive query. So we would denormalize our data by basically continuing to store the video name and the video description within our search index. And that, of course, is going to take up more space, meaning that we can't partition in the way that we necessarily completely wanted to. So rather than taking a super popular term and trying to fit it all on one node, what we can do is actually repartition that over a few different nodes and then make some client-side optimizations that know to actually check all of those nodes and aggregate them together. So internally, ideally something like Elasticsearch would do this for us, but the idea would be, you would take a term like Jordan, and then in reality, we would shard that via Jordan $1, Jordan $2, Jordan $3, and that way we can kind of repartition our popular terms. So again, what this also is going to mean is that if we do keep our data denormalized, right, if we store the actual title and the description of the video within our search index, now all of a sudden, if we want to be able to edit those, that's going to get super expensive, right? Because now we have to actually find where they are in the search index and go ahead and change them. The question is, do we actually care? Probably not really, because at the end of the day, the benefit of denormalizing our data within the search index for reads and for viewing videos is a lot bigger than kind of the cost of having to have slow uploads or slow edit speeds for our video descriptions and titles. So what would that actually look like when we bring it together? Well, let's imagine we have our user videos table, which to remind you is like a user ID, a video ID, a name, a timestamp, probably first timestamp, then name, then description, blah, 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 blah. We can actually upload first to this table, then use change data capture to go ahead and derive another table off of it, where we first shard by our video ID. And as a result of sharding by our video ID, we can ensure that the Flink instance that reads this data is actually going to have the old video name and old video description on it. And so if we know the old name and old description, then we can actually go to Elasticsearch and specifically tell it to remove that video name and description. Elasticsearch would then reach out to the proper partitions, remove them, and then also write the new ones. Now, of course, this is going to be pretty expensive, right? We might even find ourselves writing to 10 different partitions at a time. That being said, A, it's doable. B, we don't really care because even if it takes a couple minutes for that video name change to propagate to other users, it doesn't really matter as long as they'll eventually see it. So this does seem like a feasible solution personally. Of course, as always, if you guys in the comment section have a better idea, I'm open to hearing it. And then, of course, finally, we've got this absolute behemoth of a diagram. So let's go ahead and talk about it. The first thing that I'm going to start with is going to be the top left. So if we're looking over here, we've got our load balancer, which goes to our horizontally scaled user service. The user service is going to be responsible for both the users table as well as the subscriber table. So the user table is going to be sharded on the user ID. Because this is not something that's probably going to be a bottleneck, I think just using MySQL and partitioning that and replicating it in a single leader fashion is going to be fine. Additionally, we've got our subs table, right? That can be fine with MySQL. We don't really subscribe to channels that often, right? Maybe once a day or something. And so write speeds are probably not going to be the bottleneck there. More importantly, I just care about correctness. So as long as we shard this guy on user ID, right? Not who they're subscribed to, but who is actually doing the subscribing, we can use change data capture to eventually put this into our Flink node over here. So it is eventually going to fall over there. Additionally, we've got our comment service, right? For a given video, we have the ability to comment on it. And as a result of the fact that certain videos may have a lot of comments, I think that using the increased write throughput that Cassandra gives us could be very good. All we have to do is shard by the channel ID and the video ID, and then sort on the timestamp of the comment, and we should be good to go. Keep in mind that Cassandra will actually present problems if we start to try and edit comments or start to have child comments, but I would consider that more of a stretch goal. Worst comes to worst, we could always use single leader replication and then just add more partitions. I think that would be pretty feasible as well, though it may be a little bit more expensive. Finally, the most important piece of the puzzle is going to be the upload service. So the first thing that we do when we're uploading is we're going to upload all of our chunks to S3. From there, we're going to do two things. Our upload service is going to put the actual video metadata, such as the number of chunks, the name, and the description in Kafka, and it's actually going to put references to the chunks in RabbitMQ. RabbitMQ is going to allow us to efficiently load balance the processing of these chunks to our chunk processing nodes, which are going to read them from S3 all the way over here, and then ideally write them, or rather write the result of them, right back into S3, and again put the references of those into Kafka before they actually dequeue them from RabbitMQ. Once those chunk processors actually go ahead and do that, we've now got all of these chunk completed events in Kafka. And so the idea here is that the chunk completed events are going to have access to the user ID that's posting the video ID of the video, and as long as we shard on user ID, then what we can ensure is that Flink knows for a given user, num subscribers, it knows the video num chunks, and it knows the chunks that are completed, chunks completed. And so once all of those things are done, it can perform all of the external events that it needs to do. As long as these are idempotent, this should be totally fine. So of course, the first thing that we would want to do is actually upload to the video chunks table. Remember, order is going to be important here. This is going to be number one. Number two is going to be uploading to the user videos table, right? That is going to help us out quite a bit because now it's going to say, hey, this video is actually accessible. Once you click it, we're going to start reading from the video chunks table, and that'll tell us what to read from S3 on the client side. Number three is if this user is a popular user, if they have a lot of subscribers, we can read from the CDN. And then last but not least, from our user videos table, we can do some sort of change data capture, which basically says, hey, we know all of these users have videos now. We can see that one of them was either uploaded or, if I'm a client and I'm writing over here to actually change the name of my video, it's still going to flow through this same exact pipeline. We're then going to go into this video metadata queue, which of course is going to be Kafka so that we can use Flink again. we can go ahead and shard on the video ID itself so that we have access to the old name and old description of that video. And then of course we can make whatever removes or adds to Elasticsearch that we need to make. I have Elasticsearch as one big circle here. Right now I want to keep this abstract because I'm going to go into a lot more depth on it in a future video. But the gist is Elasticsearch is probably going to have to write to a bunch of different partitions, and that's okay. We don't really need this to be fast, we just need it to work. The only thing that we really need to be fast is this guy right here, reading from S3, reading from the video chunks table. In reality, there would probably be some sort of caching layer on the video chunks table, particularly for popular videos, but I've chosen not to go into that too much because we've already seen how caching is going to work in a distributed setting. Anyways, guys, wow, this was a long one. So far, the longest by far. And yeah, great stuff. Thanks for hanging in there. My voice hurts, so I'm going to go drink some water. My throat hurts. Geez, I can't even speak. I'm losing it. And I am now going to go to sleep. So with that being said, have yourselves a great week. I hope you enjoyed this one, and I will see you in the next one.